Good morning, everyone. My name is Dr. Shane Johnson from the University of Michigan and Shanghai Jiao Tong University Joint Institute. Let's get started. This course teaches a lot of the basics of structural and solid mechanics. That's helpful for a lot of different disciplines, like you can see on the slide here. Civil engineering, mechanical engineering, and aerospace engineering especially have an area of overlap that I've highlighted in pink in this slide. So it's structural engineering and civil engineering, solid mechanics and mechanical engineering, structural engineering and aerospace engineering. These areas have this course as a foundation. So many of you who are taking a class like this, you may think, well, what's coming next? What's the what kind of jobs could I have if I go through a class and spend a lot of time and learning this content? Well, you learn the basics of how structures work and how things break and fail and how we design those things to prevent their failure, and especially catastrophic failure, so that people don't get killed in the structures that we build and that we design and build. So in civil engineering, that could be a roadway, it could be a bridge, it could be a building. In mechanical engineering, that might be a car frame, that might be a rail, the body of a rail system. You could also have in aerospace engineering helicopters and fixed-wing aircraft. So those are all different structures that we would typically think about, but your cell phone is a structure. Your body is a structure. And the fundamentals of those structures is in solid mechanics, and that's a lot of that is taught in this class, and then it's expanded upon in more advanced classes in these different engineering disciplines. I didn't include here a few others. Biomechanics and material science also have some foundation in solid mechanics, and that helps us to understand how materials work. So the mechanics of materials section of this class is also a basic class for all material scientists as well. So no matter what of these 4 or 5 or so disciplines, it's helpful to know this, the knowledge from this class. In addition to that, even you buy a house one day, or you buy clothing, you buy a ring, when you get married, or other things. You can look and see where things might fail from just understanding how the knowledge from this class. So that's really helpful for just everyday things as well. It changes your lifestyle when you see how systems work and what is more elegant and more efficient in design. How do you when you buy luggage, how can you make it lightweight? There's a lot of really interesting things to solid mechanics. So I hope you enjoy the class. In these areas, you can see, although JI has some material science and mechanical engineering that cover these two topics, you can still branch out from there to many industries and many areas of engineering. And that's quite exciting. Thanks. Let's get started. We'll get started here with force vectors and force resultants. So you see how vector math works, and so we take a vector, we take its components in Cartesian coordinates. Many times we add these or combine these vectors together to get a force resultant. So we start that way, and that yes, there will be different units, pounds and newtons, and we're going to see how we mathematically represent those forces. What do they physically represent in terms of maybe forces in a cable, or forces or moments in beams or other things, and then we see how to use that vector math towards physical problems and physics problems. So this is the basics and most foundational part of the course, and so you really have to have a good understanding of this. There's other ways that we go about doing this with some geometrical rules from trigonometry that we may remember using parallelogram or triangular rules. So this is chapter 2. So force vectors, force resultants, how to use the parallelogram rule, how to use the triangle rule, law of sines, law of cosines, making sure that we know how to draw somewhat of a free body diagram simply, and then how we go about adding vectors and then how to combine forces to be able to get at resultants. So that's what this chapter is about. It's also how to get forces have both a magnitude and direction. So we want to see how to calculate the magnitude from a vector. Some of these are prerequisites, but I go over that a little bit here in this lecture as well. And that's coming just now. Thank you.
Force is a vector quantity that has both direction and magnitude. So forces can be added, like the example of cables on a cable-stayed bridge. The forces that are acting on the columns, or forces that are acting, for you in your seat, or on of the seat to the ground, for example. They can be added to give a combined resultant force. So that helps you to understand what is the force of you and maybe your chair combined on the ground, right? So that's a total or magnitude of forces. So we commonly combine forces to better explain how objects are acting between each other. So forces can be combined to obtain a resultant force. We can do that using a parallelogram law, or we can also use rectangular coordinates to be able to add vectors together that way. So I wanted to look at an example of how to do that, and so the Hibbler text that we're working with this semester has a nice example of an eye bolt, and so this little object here is an eye bolt, and coming out from the eye bolt are two cables, and you can see that like a rope connection, or a braided or twisted rope connection with a nice bracket on there to hold it on, and then you have a force coming out of it. So you have for a cable, you have one force acting along the length or direction of the cable. For this example, you have the eye bolt tied to the ground, fixed to the ground, and then you have two cables coming out, one at 15 degrees from the horizontal of 100 newtons, and the other 150 newtons at 10 degrees from the vertical. So from this, you could use the parallelogram rule to calculate what is the resultant force from combining these two vectors. So just to help us out, if you can recall, we had the sine law and cosine law given to us previously, but let's try to use the parallelogram rule to get us started. So what it would say is that we let me try this out, is that we can reproduce this this combination of forces here. Let me just send this to the back. So we can reproduce this system of forces by the vectors shown here, and then the parallelogram rule would say we're going to take one of these vectors and we're going to place it on the end of the other one. We can then take this first vector and put it on the end of the first one, and we have a parallelogram. Now, if I join from the start of these to the end, then that would be my resultant, right? So let's label this one the F, and we can have a little sub R here, so subscript R, or I can have a little capital R. So this is a force resultant, right? Next we will label the angles here. And so here we have 10 degrees. And from this we have some basic geometry that we can find the this angle here. And so we have that we can say 90 degrees minus 15 degrees minus 10 degrees equals 65 degrees. So once we have that, we also know it's a parallelogram. So we have that this here, and we can call this theta 1 is equal to 65 degrees. And the corresponding angle over here, then it must also be theta 1. So the summation then of all of the angles, the interior angles of this parallelogram, then must equal, the summation must equal 360. So we have 360 minus, and right now we're trying to find the, let's say, theta 2 and theta 2 here. So we have 360 minus 2 times theta 1. That will give us these two here, the summation of those two. So we'll have to divide by 2 to give us theta 2. So then this one should be 360 minus 2 times 65 degrees divided by 2. That will give you the theta 2. So that would be 115 degrees. Okay, so now we have we know theta 1 and we know theta 2. What we don't know is these interior angles. So you can see that maybe we can use our cosine law or sine law to help us to get those other parts. So we have a few. What we would want to know is we want to solve for this force resultant and possibly what is the angle of that force resultant. Unfortunately, we don't exactly know. We only know that this is 15 degrees and this combined angle is 65. Okay, so we know the we can know the theta 2 though, and we know what these two sides are. So this is 150 newtons, and this one is 100 newtons. So we know two sides and the angle that's opposite of this one. And then, but we don't know FR. This is what we want to solve for first. We would also want to solve for what is this small angle here, and then the angle from the horizontal. Okay, so coming up to these law of cosines and law of sines, we can see, well, if we know the, for example, B, and we know C, and we know A, then we can see what is this A. Now this one, by corresponding, if we say this C is actually F sub R, right? So we would know, for example, A, we know B, we know C, so then that can tell us what is the F sub R here. So let's do that here. F sub R is equal to the square root of 100 newtons squared plus 150 newtons squared minus 100 newtons times 150 newtons times 2 times cosine of theta 2. Let's just continue that out. So F sub r is then 212.6 newtons. Given some better significant digits here, I could also say 213 newtons, and that would be more correct, since at least we're given 3 significant figures in the problem. Now, so that's F sub r using the parallelogram rules here. Now, how would I solve then for the angle that's here? So we want this angle. Let's call this one, for example, theta 3, for example. So if we want that to solve for what is theta 3, then we can use the law of sines. So in the law of sines, and I can come up here to just show you that again. So we have A over sine of angle A is equal to B, or length B, over sine of the angle B, and then so on for C. So the side C is directly across from the angle. So the side A is directly across from the angle A. So that just kind of helps you to know how to go about using that. So what we can do here is we can say, now that we've solved for F sub r, we can say the F sub r divided by the sine of theta 2, because you can see the opposite to the angle theta 2 is the force resultant F sub r, is equal to, now we want this theta 3, and opposite of that is the 150 newtons. So we'll have 150 newtons here, and we'll divide by the sine of theta 3. So now we need to solve for the theta 3. So what we can do is just to rearrange everything to solve for the theta 3. So that would give us 150 newtons times sine of theta divided by F sub r is equal to the sine of theta 3. So that's that, and so you can solve then for the theta, and that's using the law of sines, and I'll let you do that. And so next, you could also get there a different way, which is that you could solve for theta 3 using the rectangular coordinate system. So with the rectangular coordinate system, we can just add the components of the vector. So the 100 newtons, breaking that into its x and y components. And then you can add it directly to the 150 newtons, so the 100 newtons in its direction, plus the 150 newtons and its direction. So you can add those rectangular components together, and then you can get the magnitude directly through some distance rules. So let's go ahead and do that, so you can see how to go about doing that. And so that's the F sub r would be equal to, here we go, just 100 newtons times the cosine of 15 degrees plus the 150 newtons. And you can see that is the 100 newtons is the 150 newtons is the one that's more vertical here. So the x component is then the sine of that angle, 10 degrees there. So sine of 10 degrees. We'll put that in parentheses, and this is in the I direction. Now, then we can add to that the coefficients, the rectangular coefficients for both forces in the y direction. So for that, we're going to do 100 newtons times the sine of 15 degrees plus 150 newtons times cosine of 10 degrees. And that's the J. Okay, so this is the force resultant here, the force resultant vector. So this is this accounts for both magnitude and direction. Now, if we wanted to solve for the magnitude only, then we can easily solve for that as well. And so that would just be that you're going to let me scroll up a little bit here. That you're going to take the magnitude of f sub r. So to show that, we put f sub r in these straight brackets. So this means the magnitude of f sub r, and then we can take the square root of 100 newtons cosine 15 degrees plus 150 newtons, this should say newtons, sine 10 degrees, and we'll square that, plus 100 newtons sine 15 degrees plus 150 newtons cosine 10 degrees squared. Okay, and that'll give you the magnitude of the resultant force. Now, if you wanted to solve for the angle of the force from the horizontal, you can just use tangent to be able to get there as well for the different rectangular components. So that would look like, for example, I have the, to get that angle, tangent inverse of, well, 100 newtons sine 15 degrees plus 150 newtons cosine 10 degrees divided by 100 cosine 15 degrees plus 150 newtons sine 10 degrees. Okay, and this will give you the angle theta, which would be from the horizontal. And so just coming back up here, that would be that this would be the angle theta. So that's helpful for both Cartesian coordinates. You can find the resultant angle from a horizontal, and you can also find the force resultant magnitude. It's helpful to do the parallelogram rule using law of cosines, law of sines, especially to visualize problems and to understand where the coefficients come from. It's also helpful to use the rectangular coordinate system, and that helps you to solve problems as well.